In this video, we talk about Boolean identity and canonical forms. Boolean identity, we know that a digital computer contains circuits that implement Boolean functions. The simpler that we can make a Boolean function is, the smaller the circuit that will result. There are many benefits and advantages when we have the simpler Boolean function, because with simpler Boolean function we can build a simpler circuit that's much cheaper and also consume less power and run faster than the complex circuit. With that said, we always try to reduce or simplify our Boolean function to the simplest form, and Boolean identity will help us to do that. The first basic group of Boolean identity we will discuss here is consists of four identity laws. The first one is the identity law. So in the n form, we have the x and with 1 equals to x. And in the or form, we have x or with 0 equal x. In the null law, indicate that when x and with 0 equals to 0 and x or with 1 equals to 1. Idempotent law say that when x and with x equals to x and or in the or form x or with x equals to x as well. In the inverse law, we have the x and with x complement equals 0 and x and with x complement equals to 1. Okay, so that's the first group of the Boolean identity. The second group of the Boolean identity should be familiar to when you study with the algebra. The first law we discussed it is a commutative law. So it indicates that the order of a variable in a Boolean function is not important. For example, in the n form, when x and with y is equivalent to y and with x. Similarly, in the or form, we have the x or with y the same or equivalent to y or with x. In the associative law, we have the order of a group of variable. Operation is not important. When x and with y and then and with z is the same or equivalent to x and with y and with z. Okay, so where y and z gonna be and together first before we perform the and operation with x. Similarly, we have in the or form x or with y and then or with z is equivalent to x or with y or with z. In the distributive law say that x or with y and z is equivalent to x distributive to this the n operation is in x or with y and x or with z, and the result to or operator gonna be n together. In the or form, when x and with y or with z is the same with the x or with y and or with x and with z. Okay, so that's the second group of the Boolean identity. The last group of the Boolean identity is the perhaps the most useful using for Boolean function simplification. So in this one, we have the first identity is the absorption law. So it's saying that when x or with y and z equivalent to x. In the or form, we have x or with y, x and y equal to x as well. That's absorption. So the whole thing gonna be reduced to x in the n and or form. The Morgan law saying that x and with y is equivalent to x complement or with y complement. In the OR form, we have the x or with y and the whole thing complement equal to x complement and y complement. Okay, and in the double complement law, saying that a Boolean variable x have the double complement gonna be obtain the original variable x itself. So now let's look at a specific example to see how the Boolean identity can be used to simplify the function. Let's consider the function f of three variable x, y, z equal x, y or x complement z or y, z. Right, so the first step, we can use the identity law, and we can transform yz equal to yz and with 1. Okay. In the second step, we're gonna perform using the inverse identity. So we're gonna transform 1 gonna equal to x or with x complement. Okay, the whole thing here is the same. The next step, we use the distributive law. We're gonna distribute yz into the OR operation right here. So we have the yz distributed in gonna be yz x right here, and or with the yz x complement. Okay. The next one, we use the commutative law. So we can switch the order of the variable here. So we can see y, z, and then x is the same with the x and y and z. And we all with the same right here. We all with x complement and zy. The next identity we use to simplify the function, that the associative law. So we can see that x, y, and x complement z, or with this one gonna be transformed into x, y, and then z. The same here, we're gonna have the x complement z and y. Okay. And then we use the commutative for the OR form, so we can switch the order of x complement z right here, and just back to this order, and we're gonna move the x, y, z into this order. Okay. And then we the next step, we use the distributive law, so we can put yz outside right here, and the inside we have the 1 or with z. Okay, so for the first two component of the Boolean function can be transformed into yz and with 1 or z. Okay, the last two components of the Boolean function can be transformed into x complement z and with 1 or y. Okay, so based on the null law, we can see that 1 or with z equal to 1. 1 or with y equal to 1. Okay. And the last step, we use the identity, so we can see that y, x, y, and 1 gonna equal to x, y, and x complement z with 1 equal to x complement z. Okay. So you can see that the Boolean function f right here have the three components. Now we can simplify it into only two complements. Okay. In practice, we also can simplify a Boolean function by using the complement operation. And sometimes it is more economical to build a circuit using complement of a function, and then use the function to revert it. So the Morgan law provides an easier way of finding the complement of a Boolean function. So the Morgan law saying that when x and y and the whole thing complement equal to x complement or with y complement, and in the OR form complement, we have the x or y complement equal to x complement y complement. Okay. In case of multiple variables, we also can perform complement operation the same way. Specifically, we can replace each variable by its complement and change ON to OR and OR to AND. Okay, let's see a example. We have the function f is a three variable xyz equal to xy or with the x complement y or with the z complement. So we have the f complement function gonna equal to the whole function right here complement, and we're gonna transform each of the operator right here become the AND operator right here, and where each of the component inside right here gonna be perform the complement. Okay, so we have the xy gonna become xy complement, x complement y gonna become x complement y and the whole thing complement, and with the xz complement and now become xz complement and whole thing complement. And we using the De Morgan law, we can obtain xy complement equal to x complement or y complement. Okay, we transform the AND operation right here, we become a OR operation. The same right here, we have the x complement y and the whole thing complement equal to x double complement, so it become x, or with the y complement. And the last one, we have the xz complement and the whole thing complement equal to x complement or with z double complement, so equal to z. Okay, so that's the complement of multiple variables. So basically, we transform n to ORs and OR to n, and also we perform complement for each of the variable or components of the function. Canonical form, there are a numerous way of stating the same Boolean function. So, for example, we can see that the function variable we see before, there's many ways to represent it. So the synonymous form are logically equivalent. So it's mean they have the identical truth tables. So in order to eliminate the confusion as possible, so the designer expressed the Boolean function in standardized or canonical form. There are two canonical forms for Boolean expression: the sum of products and the product of sums. We recall that the Boolean product is the AND operation and the Boolean sum is the OR operation. So in the form of sum product, and variable are all together. So for example, the function f of three variable x, y, z gonna be represented by x and y, or with x and z, or with y and z. So this is the sum of product. We have the sum right here, and this is the product right here. On the other hand, in the product of sum form, all variables are AND together. So, for example, the Boolean function f of three variables can be represented by x or y, and with the x or z, and then and with the y or z. Okay, so we can see that the OR form and with the other term in the in this parentheses. The sum of product form is easy to represent if we know the we have the truth table of the Boolean function. So, for example, we have the f Boolean function f of three variable equal x, z naught, or with y. So in order to transform the Boolean function in the sum of product form, we first of all we transform or represent the function f in a truth table where we already care about the variable that make the function equal to 1, or that's a true value. Okay, so the truth table of the variable of the Boolean function is represented right here. We have the three variable x, y, z, and the output gonna be represent the value of the function f. So we can see that when x, y, z equals 0, we have the output of the function f equals 0. X, y, z equals to a 0, z equals to 1, and the function is going to equal to 0, and so on. Okay, so by using the input variable right here, you can plug into the function right here and compute the value of the f function. And based on this one, we can represent the function in a sum of product form by sum of the product form of the variable together. So specifically with the function f in the with the truth table in the right hand side right here, we can represent the function f equal to the first term gonna be correspond to this value 1. So that's gonna be x complement and with y and with z complement. So this first term right here, and then we OR with the next term that make the function f equal to 1. So that correspond to x complement and with y and with z. So that's the second term right here. The third term gonna corresponding to this row right here. That's x, y complement, z complement. The next one gonna be a x, y, and z complement, and the last term of the sum of product form of function f gonna be a x, y, z. Okay, so based on the truth table, we can represent the function f in the sum of product form easily. But one note that we can easily can see that this function is not a simplest form. Okay, and our aim is only to write our function in the canonical form of product. To simplify this one, we can use different technique. One of the technique we just discussed before, that's using the identity to simplify a Boolean function. Later on, we also can will discuss how to use the K-map to simplify a Boolean function. Okay. So that's it for this lecture. We can discuss more in the next lecture. Okay.